A great way of grokking Git commands is to understand how it behaves internally. In this part, we'll show you how Git's internals are actually quite simple, contrary to what its wealth of features might lead you to believe. Linus Torvalds, when inventing Git, had a simple proposition. It manages files and directories, so its internal representation should be like a file system. A Git repo has four main object types. At the lowest level are files, represented by objects called blobs, a common computer term that stands for binary large objects. Every non-empty directory is represented by a tree object that describes the blobs and trees it contains. Then come the higher level objects, commits and tags that shape our history graphs and its metadata, descriptive information such as the commits message, date, author, committer, etc. You will also come across the notions of commitish and tree-ish that often show up in the docs. Commitish means anything that unambiguously leads to a commit, so commits themselves and tags. Tree-ish is the same for trees, so a tree proper or a commitish, as commits reference their root tree. Git is an example of a content-addressable file system. This means the identity of an object is directly based on its contents. To do this, Git uses a hash function named SHA1, pronounced SHA1, where SHA stands for Secure Hash Algorithm. It can distill any content into a unique 160-bit digest, usually represented as 40 hexadecimal characters. Note that SHA-1 was deemed insufficiently secure back in 2005, and Git is in the process of adopting SHA-2 instead. This type of key is sometimes called a fingerprint or checksum. In Git repos, file names for all four object types derive directly from these keys. For a blob, its identity is based on a relevant file's full content. Let's say we have a file in our current working directory. We then add it to our Git repo, yielding a blob whose name is the identity that the hashing function produced based on file's content. Now, let's take the lines in that file and copy them exactly in another file, say a subdirectory of our project. Then let's add it to the Git repo. Git will reuse the existing blob, as both files are exactly identical. However, should I modify one of these files and commit it again, it would yield a new blob for it, as the fingerprint is different and unknown so far. Trees are added to the repo at commit time. Here you can see that two tree objects are created, one for the project root and one for the subdirectory. If we look at the tree object for the root directory, we can see that it contains a reference to the tree for the subdirectory and a reference to the blob for file A. It only contains data for its immediate contents, and these data define its identity. In the same way, looking at the tree for the subdirectory, we do see a single reference, this time to the blob for file B. Our previous schema wasn't comprehensive. A new commit indeed yields a commit object for it in the repo. If we look inside that commit object, we'll see a tree object for the project's root, possible parent commits, then various metadata such as the author of the commit, its committer, and finally the full commit message the author typed in. Again, all these data define the commit's identity, so any change in the timestamps, message, tree, and so forth will yield a different commit object. As parent commits also show up in there, they impact a commit's identity. This is why you sometimes hear that commit's SHA-1 identifier represents not just its contents, but its entire history, and why moving a commit across the history graph changes its identity. Earlier in this course, we looked at the lifecycle of files and said that adding a file to the index snapshots it. What does that mean exactly? Let's say we work in the newsroom of a newspaper and our local repo stores photos for the next issue. A commit would then hold the photos for an article. Let me introduce Billy, who's a resident file photographer. She's tasked with taking photos of the files you request for your articles, and she then lists the one you end up selecting for publication on her whiteboard. Hey, here comes a first file to take a photo of. So we ask Billy to take a photo of it, she does, and her camera gives her a file capture and provides a reference for the photo. Remember that thing about SHA-1s? She then places the optimized photo in the newspaper's asset bin, then jots down on the whiteboard the reference for the photo and its original name and location. Now comes another file that we also want in our article, and again, Billy snaps it and writes down the reference in her list. Billy's action build up our Git index. She takes snaps on request, puts them in a temporary storage, and waits for a commit to use them. As we just saw with the index, our Git usage produces files with obscure, hard-to-memorize names. SHA-1s are really not meant for humans. This is why there's a whole system of references to help us work with them. There are multiple complementary reference systems. We saw that the index lists references to objects in preparation of a commit that in turn grabs them and also holds references to one or more parent commits. A history is therefore made of the relationships between commits. The head reference targets the current commit, that is, the one our ongoing local work is based on, or put differently, the one our next commit would use as parent. This reference is often indirect, as it references a branch that in turn references the actual commit. Long story short, any commit creation or movement across our history moves the head, hence updates the relevant reference. A branch in Git is just a label referencing the latest commit in the part of the history it designates. You'll often hear branch tip for this too, which is perhaps easier to visualize. A tag, like a branch, is but a label referencing a commit, but it is expected not to change over time, unlike a branch tip that tracks the progression of the branch's work. You'll sometimes see annotated tags that are actual objects with not just a commit ref but also specific metadata. Let's recap that using a nice animated diagram. So, starting from our base objects, let's see how references add up to our Git history. We start with the blobs, representing our files. Then come the trees that represent our directories and reference blobs and other trees. Every commit references a tree for the project root. Adding commits builds up our history. The first commit sets up a first branch, whose name defaults to master. It really is a simple label referencing the commit. There's another critical Git reference, head, whose purpose is to let us know what our current working location in the history is. Right now, it references the master branch. We add some more commits, building up our history, every commit referencing its parent. Now, say we create a dev branch. We can see we're really just creating another label referencing the same commit as head. Notice we created the label, but head doesn't reference it yet. Therefore, it is not our active branch. So let's switch. Let's ask head to reference the dev branch so we can start working on it. And let's add some commits. We can now switch head back to master as we intend to merge the work with it on the dev branch. Executing that merge yields a merge commit with two parent commit references. We could tag this as version 100 now that the feature is merged in. And now, if we create a new commit on master, you can see the tag holds still, but the master branch tip moves along, tracking further commits. Finally, now that our dev branch is merged, we could decide to remove it. This just requires removing the label in the repo. It doesn't remove commits in any way.